Okay, so hello everyone, welcome to the 7 days online training program on Google Earth Engine for remote sensing analysis. So basically, today is our fourth number days. I will try to explain all this topic for that. And after completing the 3 hours live training program, then we talk about that problem solving class for 1 hour. Okay, so in the problem solving class, simply you can share your problem with me. Just simply share your screen and then show me your problem. Then we try to discuss about the solution about that. So let's go. Let me share my screen. Okay, can you see my screen? Is it visible? Can you see my screen? Okay,
Yes, sir.
okay, thank you. So now continue. Yeah. So basically, today's session I discuss about that how to remove cloud and haze from satellite imagery. So basically, when you work with rainy season or you work with some place where almost all time we find out the cloud, so then we find out in the cloud in our satellite imagery. But in Google Earth Engine platform, we can easily apply and further we can easily remove the cloud and haze from our satellite imagery, and then we can easily get very neat and clean satellite imagery. Okay, I also ready to show you that Landsat Sentinel, both of satellite imagery, how we can easily remove the cloud and get the very neat and clean satellite imagery. Then we talk about that DEM data, basically digital elevation model data, how we can easily use in Google Earth Engine and create the different types of topographical mapping such as hillside map, slope map, aspect map, elevation map using NASA SRTM DEM as well as also ASTAR DEM. How we can easily use, we also discuss about that. And another thing is that LST monitoring, basically land surface temperature using Landsat satellite imagery. So previous class I'll discuss about the MODIS satellite imagery, but MODIS have a problem. This problem is that when you are using the MODIS in a small study area, we find out the grid or cell. We don't find out the smooth map because MODIS resolution is not good. MODIS is 1000 meter or 1 kilometer resolution or pixel size. So that's why when you monitor the LST, then we must need to use the Landsat satellite imagery to get the more better result for a small study area to generate the more better map. Okay, using the Landsat imagery we can easily find out that. Okay, so that's why in this case I also try to show you that how we can easily use the Landsat satellite imagery to monitor the LST. We also discuss about that, and how to calculate average, maximum, minimum NDVI for any specific region. Suppose I have agricultural land. So now this agricultural land I want to monitor NDVI temporal analysis. Basically when plantation phase or pick up the growth phase, okay, or harvesting phase. So then we find out a pattern when you identify, make a time series chart for your agriculture monitoring or agriculture crop monitoring. We also use this type of things. I have to discuss about that, and how to monitor the urban heat island, because urban heat island is also defined on the LST, land surface temperature. So that's why in the same time I also discuss about that urban heat island, how we can easily monitor and identify this place is urban heat island, this place is urban heat island. So just we identify this type of place, and also discuss about that urban thermal field variance index. So it's one kind of index. It describe about that impact of urban heat island. Okay, what's the impact, where the high impact of urban heat island we can easily monitor using this index UTFVI, urban thermal field variance index. When we apply, then we can easily identify where we find out the high impact of urban heat island, where is the low impact, what is the moderate impact. So we can easily make the classification, also make the map. And how to make LST time series chart, we also discuss about that. So let's go one by one. I will try to explain all of topic. I hope we can easily get it. So first of all, I will try to explain about that LST, how we can easily monitor the LST. And if you simply search on the Google, or you can simply visit the Google Scholar and simply search, we find out a lot of paper related to the LST. Suppose I simply search land surface temperature, Landsat, simply search. So we find out the lot of paper regarding this type of topic, land surface temperature. Okay, just a minute. Let me share again. Okay, so you can easily find out a lot of paper regarding this type of topic. So estimate the land surface temperature in the Delhi study area, online global land surface temperature estimation from the Landsat. So you can see there are a lot of paper already published using the land surface temperature related topic. Okay, if you check, suppose, so you can find out. Okay, so you can see the modeling impact of the land use, land cover pattern, urban thermal field variance characteristics, as well as land surface temperature or urban thermal field variance index. Okay, Dhaka metropolitan area. Okay, so you can easily find out the lot of paper is already published. Not only for that, if you check it, so this is the land surface temperature related paper. So basically they are make the combination land surface temperature and land use, land cover. Okay, so today's we discuss about that land use, land surface temperature. When I talk about that land use, land cover, then you can easily relate it. Okay, and then you can easily publish this type of paper. Okay, related to the land use, land cover, and also land use, land cover, and also LST. Okay, so you can easily find out lot of algorithm. So suppose I want to focus, almost all of algorithm are the similar. Okay, not much difference, but almost all of algorithm is the similar. So if you check it, this type of algorithm, so here you can see basically they are calculate. So this is the main equation about the LST. So basically you can see they are TB mainly brightness temperature. Okay, satellite brightness temperature. Then you can see one, it's a constant value, lambda mainly it's the wavelength of emitted radiance value, and rho basically this is the constant value, 1.438 multiply with 10 inverse 2, and also emissivity we also calculate. Okay, and this is the equation. When you calculate, then we can easily calculate the LST. Okay, not only for that, if you check the other paper, suppose I simply search LST using Landsat, simply search on the Google Landsat 8. So you can easily find out, just simply click on the image, then check. Suppose you can see it's one kind of algorithm. Okay, let me open it from the ResearchGate. Okay, so this is the one another work for using the Landsat 8 satellite data to monitor the LST. So basically in this case you can see, if you check the flow chart, basically they are used at the band 10, band 5 and band 4. So band 5 and band 4 they are used for NDVI. After the NDVI they calculate the vegetation proportion or vegetation fraction. After that calculate the surface emissivity using the brightness temperature, and further there apply the mono window algorithm and then calculate the LST. Okay, so it's a kind of algorithm, and there also compare the data. You can see Moody's LST data and also Landsat data, just calculate the regression. So these things I also added, but another way. So how we can easily calculate the regression, y equal to mx plus c, this type of data. Suppose in this case they make the correlation. Okay, so you can see they find out the R square value is the 0.723. So this type of things how we can easily use, I also try to show you that for other class, basically 2 more class inshallah for the air quality monitoring. Okay, this type I also added for linear regression model. how we can easily create, and also calculate the y equal to mx plus c, and also calculate the correlation coefficient or r square value. We also discuss about that. So let's go, we try to follow. So if you check this algorithm, first of all you need the Landsat 8 satellite data, and we need the band 10, band 5 and band 4. So let's go try to follow this type of step and then write the code. So let me open my code editor. So I want to work with Landsat. Click on the Landsat image collection. In the Landsat 9, Landsat 8, Landsat 7, all are the same process when you work with LST. Same process, because it basically is the time period. Okay, so you can see the Landsat 9 is available from this time, Landsat is available from this time, Landsat 7, Landsat 5, Landsat 4, Landsat 1 to 5. It's different time period. But when you apply this type of things for other Landsat image collection, just apply the same process. So let's go, I want to work suppose Landsat 8, and I want to use for the open land imager OLI data. So from here we try to use for Landsat 8 OLI data. You can see this is the surface reflectance data we try to use for monitoring the LST for surface reflectance. Just click on here. Okay, so this is my data set about that Landsat 8 level 2 data. So this data I want to use, and you can check this is the band name is the STB10. So STB10, it's called the brightness temperature or band 10. Okay, just okay. Can you hear me now? Hello.
Yes, sir.
Okay, okay.
Yes, sir. Yes.
Okay. Okay, so here we find out this is the Landsat 8 image collection, and mainly we need this type of band STB10, and so need the SRB4 red band and near infrared band. Okay, so we need that SRB4, SRB5, and also need that STB10. So this three band we need to add, okay, in our work for the LST. So let's go try to add and then filter the image collection. So first of all, we already know about that how we can easily filter. Just copy the snippet ID and then paste on your code editor. Then just give a name, just give a variable name. Suppose I put the name is that image. Okay, so now this is my image collection. So this image collection simply filtered. We already know about that how we can easily filter. So basically we need to use the filter bounce function, filter date function, filter metadata function. So this type of function you already use. And now we also need to define our study area. So which area you want to work, just simply import your shapefile boundary in asset tab, and then just work with that. Suppose I already imported the Dhaka city boundary. Just I import my study area. So this is my study area, and I want to monitor for this study area LST. Okay, so just I give a name. I put the name suppose RY. So this is my region of interest, and I want to suppose I want to display the boundary. So just add a layer of my boundary, which is RY, and also focus the given study area map.center object. So this type of function you already use lot of time. Just I write the code, suppose 10, and run the code. So now this is my study area. So for this study area, I want to monitor LST using Landsat satellite data. So here I already imported the image collection. So this image collection I need to filter. So how I can filter? We already know where you need the image. I need the image for my study area. So for where we need to use the filter bounds function. And filter bounds function, what is the argument? Argument is my region of interest, my geometry. So in this case, this geometry is stored in a variable. This variable name is ROI. So just write here the ROI. Okay. So after that, just use suppose filter metadata. Filter metadata basically filter image properties. I need only for those images which image will not more than 1% cloud cover. So my properties name is cloud cover. So right here cloud cover, then less than and 1. Okay. Then a specific time period, filter date. Suppose I want to monitor the LST for present time, suppose 2025 1st January from check the last time period. Last time is that 2025 04 13. Okay, just I use it 2024 5 04 13. Okay, so now I just filter my image collection. After filtering the image collection, first of all we need to check how much image is available. Okay, sometime you try but it display the nothing, it means that your image collection there is no image. So after filtering, always try to check how many images are available in my collection. Just use the print, and for counting just use the size function. So now it's computing how much images are available after filtering the image collection. So now we find out the total 6 images are available for my study area. This 6 images is available between this time period. This 6 images is the less than 1% cloud cover, and this 6 images is available for my study area. So now if you want, you can also use here the single date imagery, or if you want, you can create the median composite. Okay, sometime we need to use the single date imagery, or sometime you also need to create the median composite or mosaic composite. This type of things we need to create. So in this case, suppose I want to apply a median composite and then clip with my study area. Clip with my study area, which is RY. So let's go try to display the imagery. So map.add layer and call the image and run the code. So it look like this. So let we try to add the band combination to visualize the imagery. Suppose I put at the red, green, blue, stressing of 98%, and apply. And also import it. Just copy and paste after the object. I put it the layer name, suppose imagery. So now we find out our imagery. And if you check all of information, just use the print function and call the variable name image. So now we find out the all of information about this image, all of band information. You can see basically this imagery is stored total 19 bands. Check all of bands, you can see all of bands. But in this case, I want to work for SRB4, SRB5, and also STB10. So these 3 band I need to monitoring the LST. Okay. So first step, we need to calculate NDVI. Okay. So let's go try to calculate NDVI for LST. So we already know about that lot of process to calculate the different types of index. So NDVI formula is that I also write, suppose near infrared band minus red band divided by near infrared band plus red band. So when I apply this formula in this image, then we can easily get the NDVI result. So let's go try to compute this equation. So there's a lot of way. Previous class I already discussed the expression method or direct equation or normalized difference function. Okay, so let's go try to apply any one. So I take a variable, suppose NDVI, and now I put the equation, suppose I call the image and apply the normalized difference function. Okay, so normalized difference function. So now put the band name, near infrared band and red band. So near infrared band name is that SRB5 for near infrared, and red band SRB4. So now it computing normalized difference, computing SRB5 and SRB4. So it computing this equation, mainly SRB5 minus SRB4 divided by SRB5 plus SRB4. So now it compute the NDVI. So let's go try to add the layer of NDVI. So just use our map dot add layer and call the NDVI and run it. So now it's added this type of NDVI map without color. So we try to add the color. If you want, just click on here, and then suppose, and you can see it show the ND. Okay, you can see this one band, it show the ND. It's the default, it show the default, but if you want, you can also put the rename function. Suppose I put the rename and I put the new name, suppose NDVI. So now you can also check it also change. If I run the code and open it, we find out the NDVI. Just click on here, and now you can see it show the NDVI. Okay, I want to just stressing suppose 98%, it automatically show the range. And now I want to add the color. Suppose I want to add so this type of color, get it, then use this type of color, and you also use this type of green color. Okay, just I put the three color, just apply. Okay, and also just import, just copy the visualization parameter and paste after the layer name, just put here, and also put the layer name, suppose it's a NDVI. Okay, so now we find out this type of NDVI map. So basically this type of green color, it's indicating about the vegetation. Okay, so this is the first step when you compute the NDVI for LST. Just compute the NDVI. After NDVI, we need to calculate the proportion of vegetation. Okay, or it also called the fractional vegetation. And what is the equation about that? This is the equation about that proportion of vegetation. In this equation, they calculated NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value, then power 2. So now we need to compute this equation. So for computing this equation, we need to calculate NDVI minimum value, NDVI maximum value for my study area. So let's go try to compute the NDVI mean value and NDVI maximum value. So let's just take a variable. Suppose I put the variable name is that max. You can put any name as a variable, max. And now just call the NDVI. This NDVI, this variable is stored this map. So I want to calculate maximum value of NDVI from this map. So just I call the NDVI. And now I want to use a function, it's called the reduce region function. Okay, so reduce region function, this function mainly we are used to compute statistical value for any specific boundary. This statistical value can be average, maximum, minimum, standard deviation, anything. Okay, in this case I compute the maximum value from this study area. So that's why I just apply the reduce region function. And you can simply check all of argument from here. Just click on the docs tab and check it. Just simply search here reduce region. So you can see these two functions basically find out. The one is the reduce region, another is the reduce regions. Okay, only for S. So this function further I also discuss about that, how we can easily use it. So basically these things work for collection. Okay, suppose I have collection, not only for the one polygon. Suppose I have a different polygon, or I have different points, more than one points, or more than one polygon I want to compute. Then we need to use the reduce regions. But when you work with for a single boundary, in this case it's just a single boundary, then we are just apply the reduce region. So this reduced regions, further I also show you that how we can easily use it and what is the application. I also discuss about that. So this reduced region function, if you check the argument, first argument is the reducer. Okay, reducer. How to reduce this imagery. Then geometry, then scale, then CRS. Okay, it's optional or default null. So let's go try to apply. Just make a dictionary. So first one is the reducer. So basically how I can reduce. I want to calculate maximum value. So user ee dot reducer dot max. Okay, now it compute the maximum value. Then geometry. So geometry basically your shapefile variable name. So in this case my shapefile is stored in the ROI. So just put here ROI. Okay, this is my shapefile variable name. Then we need to apply here a scale. Okay, a scale is the resolution of your satellite imagery, 30 meter. Okay, then others not need. So let's go try to print it and check what happened. Just print the max and run it. So you can see it show the result one property, and we find out that NDVI 0.4. Basically this is the maximum value of NDVI for this boundary. We find out, but I need to it show as a dictionary. You can see. So dictionary basically keyword and key value. It's a keyword and it's a key value, but I want to represent the result as a number, only number. Okay, so this object show as a dictionary, keyword and key value, but I just need only the number. So for that, to extracting only for the number, just use here the values function. Okay, just I apply the values, and if I run the code, you can see what happened. So now it show the list computing. So when I put the values, it work as a list. In this list, if you check it, just only for the one item. Okay, and we already know about the 0 refers to the first item, 0 refers to the first item, basically 0 is the one. Okay, but it shows as a list. Okay, but I need only for this value, I don't need the list. So for that, just use here the dot get function and get from 0. Okay, just put here the 0 is a serial number. So first just click to the run. So now it show on computed object, and we find out only value without dictionary, without list, but it shows as a computed object. If you check, it shows as a computed object, but this object I want to use as a number. Okay, I need to use a number, and we already know about that when you define any number in Earth Engine platform, we need to use the function ee.number. Okay, ee.number. This function convert or construct the new number or any number. So just we put here ee.number, this function I define in here, and also close. So now it work as a number. Okay, number computing we find out. So now this value work as a number, or this variable, this max variable, it stored the number, maximum number of NDVI. So this same process we also apply to compute the minimum. Just I copy and then paste here. Just I simply change the variable name. Suppose I put the min mean, and also put here mean, and then also put here the mean. So now if I run the code, we find out the minimum value of NDVI. So we find out this type of value of minimum value of NDVI for my study area. Okay, so now we are just applying this formula. This formula basically NDVI minus NDVI minimum value divided by NDVI max value minus NDVI minimum value, and then power 2. So let's go try to compute this formula and calculate the proportion of vegetation or PV. Okay, so let's go try to do it. So for doing this thing, just take a variable. I put the variable name, suppose FV or fractional vegetation, or anything you can put as a variable. Just call the NDVI. So this NDVI I already compute. So this is my NDVI map stored in this NDVI. So NDVI minus mainly subtract function, subtract with minimum value min. I already compute the minimum value, and this value is stored in this variable min, min. So NDVI minus minimum value of NDVI, then divided by maximum value, basically max, and subtract with minimum value. So just put here that subtract with minimum value. Okay, and now whole equation we need to apply the power 2. So for the whole equation, just put the parenthesis start and also close the parenthesis and put here POW for power. Okay, and now just put here the 2. Okay, but you can also do it, but Google Earth Engine, when you define any new number, basically when you define any number in the Earth Engine server, we need to use the server function. And when you define any new number, then we need to apply the ee.number function in the server. So for that, just use your ee.number and then define your number 2. So now it works as a power number 2. Okay, and these things I want to just add a layer. So just map.add layer and call the fv and run the code. So now it added the fractional vegetation. And you can see it shows the NDVI. Okay, default. It default showing the NDVI. So basically, first you can see in my equation, first value is for NDVI. So that's why it show the NDVI default without not adding any rename. It show the NDVI because my equation first is the NDVI, so it automatically show the NDVI. But if I just rename it, suppose just I put here dot rename and give the new name, suppose FB. Now run the code. So now it will change all time. Suppose you computed any equation. Suppose I compute this equation. If I don't use the rename of NDVI, okay, then it automatically show the ND. Okay, ND automatically showing the rename default show as a ND. But when I rename it, then I find out this type of name. Okay, so you can see now it show about that FV in my layer parameters. FV. So now further, if you want, you can also just stressing and add the color. Okay, it's not mandatory, but I also add the color for visualization all of map. Suppose I'm going to add this type of color, then and green. Apply. And also import, copy this visualization parameter and paste it. You can also put the layer name, any name. I put suppose FV. Okay, we can put any name as a layer. So now we computed the NDVI, then we calculate the fractional vegetation or proportion vegetation. Okay. After that, we need to calculate surface emissivity. Okay, so this is the formula you can see in this paper. They are used this formula for emissivity. This emissivity formula is that 0.04004 multiply with proportion of vegetation. Basically these things I already calculated plus 0.986. So it's a constant value, these two constant value, and then we multiply and then addition with the 0.986. Then we can compute it the emissivity. Okay, surface emissivity. So let's go try to compute this equation. So now this two variable, suppose this two constant value, just we store it in a variable, or if you don't also same, so we try to store it. Suppose just take a variable, I put a variable name suppose A, and in this variable I stored the number 0.004. And when you define any new number in Earth Engine server, we already know about that. We need to use a function ee.number function. Okay, then we define the number. So just I stored the one constant value in the variable A, then take the another variable suppose B and put here ee.number, and another value is that 0.986. So these two value I simply stored A and B. So further I can simply write the equation emissivity. Just take a variable suppose EM or you can put any name. I put the emissivity, and then just call the FV, fractional vegetation, multiply with 0.004. It is stored in the A. Just put here the A, and then add with 0.986. It is stored in the B. Okay, so now we compute the emissivity. If you want to display it, just map.add layer and then call the em. So run the code. It look like that. We try to add the visualization. And you can see it show as a FV. Okay, you can see it show as a FV because in my equation first is FV, so that's why it default show as a FV band. So we try to rename it. Okay, then it will be okay. So just put here suppose dot rename, and I put the name suppose EMM, or you can put anything. Just click on here. You can see it show the EMM because I rename it. Stressing was 98%. And I want to display emissivity. Suppose low emissivity show as a blue color, greater than show as a suppose green color, then show suppose yellow, and high emissivity value show as a red color. Okay, or you can put any color combination. Just apply, and then also import. Just copy the visualization parameter for emissivity, paste here. Oh, sorry, paste after the variable name and put the layer name suppose en. Run the code. So we find out this type of result. So now we try to, okay, after that we need to calculate about the thermal band, basically brightness temperature, STP10, this band STP10, and you can see this unit is the Kelvin. Okay. And in this band, this is the scale value and this is the offset value. Okay, so these two value we need to further use to reproject the scale value for the STP10. Okay, so let's go try to use it and reproject the scale value. Just take a variable. Suppose I put the variable as thermal. You can put any name as a variable and call the image. Basically, this variable is stored at the image. Okay, you can check. I already put the variable name is the image. Sorry. And this one is image. So this image variable is stored at total 19 bands. So from the 19 bands, I simply select my specific band. Select the band of STP10. Okay, and this band we need to reproject the scale value. So for that, multiply with scale value. So this is the scale value. And this one is for offset value. So just add with offset value. Okay, so now we try to check it for thermal. Just map.add layer, call the thermal. So just on the code. Thermal means brightness temperature. Okay, it look like that. If I just stressing, that was given the 98%. If you want, you can also add the color combination. Suppose blue color, green color, greater than use here yellow color, and high brightness temperature show as a red color. Just apply and import. After that, copy the vegetation parameter and add the, after the thermal one, just paste here. I put it say thermal or brightness temperature. Okay, so we find out this type of result for the brightness temperature. Red is indicating about the high temperature, blue is indicating about the low temperature. So it's a brightness temperature. So now if you check the equation, so now for this equation we calculate all of those. Okay, suppose TB, brightness temperature, we calculate the emissivity. Okay, logarithm emissivity, basically this value already computed. Okay, and this lambda and this rho, okay, it's a constant value. Wavelength of the emitted radiance 11.5 micrometer, and rho value basically 1.438 10 inverse 2. Okay, so let's go, just we can apply this formula, and this 2273.15, when you subtract, then we find out the result in degree Celsius. Basically brightness temperature, this value is for Kelvin. So when you subtract this value 273.15, then we find out the result in degree Celsius. Okay, so let's go try to compute this equation and display the LST, final layer of LST. So for that, just take a variable, suppose LST, and call the thermal, and we just apply here the expression, and our expression is that TB, basically brightness temperature, this TB is divided by 1 plus, just normalize this value, we find out 0.00115. Okay, and these things multiply with TB, brightness temperature, divided by 1.438, 1.438, and these things multiply with logarithm log emissivity. I put suppose EP. Okay, so this is the equation we find out, and this equation just need to subtract minus 273.15. so in this equation now we need to define all of variable. Suppose TB is one kind of variable, if is one kind of variable, otherwise all of values is the constant value. So let's go try to define. For that, just use the comma sign and make a dictionary. For the dictionary, just curly bracket, and in this curly bracket you need to define what is the TB. Okay, TB basically thermal band. Okay, so just write here thermal, and we already calculated the thermal band in here, just I put here the thermal, same name. And then what is the EP? EP mainly emissivity. Okay, just write here EP, it's mainly EM. Okay, I already calculated the EM, you can see EM. So these things I already computed EM, so just I put here the EM. So let's go try to display the final map.net layer and call the LST and run the code. It should the STB10. Let me just rename it. So just put here the dot rename as a suppose LST. So run the code. Let's try to add the color and visualization. So just stressing 98%. And now just add the plated. So we find out this type of range. Suppose I am to display lower 25 or lower than 25, this type of place I want to display, suppose this type of blue color. Okay, then I need to show suppose a green color, then show suppose this type of yellow color, and 39.48 or greater than 39.48, this type of place I need to display suppose red color, this type of color. So now apply. And after that just import the visualization, just copy and paste and put the line of LST, run the. So now you find out this type of map. So this type of color indicating about the high temperature, this type of color. Okay, and it's a water body. We find out the low temperature. If you want to check the value, suppose click on the NFCT tab and click, suppose just click on here. So now we try to check for this coordinate what the temperature value. So we find out 36.49 degrees Celsius. Suppose this type of place, click on here. We find out the 25.74 degrees Celsius. Okay, click on here. So we find out that 39.81 degrees Celsius. Or if you want, you can also change the time period. Suppose I take the whole year annual. I want to check, create the map for annual. Suppose 2024, 1st January from 2024 December 31. So now you find out the result for this year of 2024. All of imagery, less than 1%, all of imagery, and create this result. Okay. So if you just expressing or I just apply, almost similar, not much difference. So you find out this type of place. Okay, we find out this type of red color place. We find out that high LST value or high temperature, this type of place. Okay, and this is the map for year of 2024. And if you just check the value, click on here, Inspector tab and click on this map. So you find out 38.75 degrees Celsius. So this is the LST map. For that we can easily export this map. For that just use here this code, export image to drive, and then put all of argument. Okay, then we can easily export this LST map easily. So this is the map for using the LST for a small study area. But when you work with MODIS for the small study area, we don't find out the better map because MODIS is not good resolution. Landsat we find out only for the 30 meter pixel area. So that's why it provide you the more better map. Okay, So this is the way to compute LST. Okay, anyone any question, you can ask me please for this topic. LST, yes please. Yes.
But in the export map, it's generally comes in black and white.
Yeah, black and white, basically when you export it show the gray color. Okay, so further we need
Yeah.
to add the symbology from your ArcMap or QGIS software. Simply go to the symbology. From the symbology we need to add the color. Okay, this process I will show you inshallah for the tomorrow class. Then you can easily get the idea how we can easily, after exporting, how we can easily create the map using ArcMap or QGIS software. Okay, no problem, I will show you.
So I just want to ask, it cannot be exported as a Google Earth. It is always in the
Yes,
grayscale
always it when you export TIFF format, any TIFF format image, always we find out the grayscale color. Okay, so visualization we cannot export it from here. Okay, we are just take the screenshot of this screen. Okay, and then use it this visualization. But when you
Then we
export,
should not bother with the visualization parameters here, sir.
which one?
Then we should not bother for visualization parameters.
Yeah, visual parameter is not possible to export when you export the TIFF format image. Okay, but we are also use the image. Suppose just take the screenshot of your screen, then you can also use it. But when you export as a gray color, always we find out the gray color when you export this type of map. Okay.
Yes, sir. Then we can
Yeah,
visualize
yeah.
this in QGIS.
Yes. So I will show you this two more class about that, how we can easily after exporting, how we can easily make the map. Same process, any kinds of gray color we can add the symbology, and then we can easily add our own color from the symbology, then we can represent this map. Yeah. Okay, so this is the way to create the LST map. So now I want to make the time series chart. Suppose it show the year of 2024, all of images less than 1% cloud cover. So now I want to check the temporal change or temporal analysis, when it will be high, when it will be low. So which day is high, which day is low, I want to check it. So for that we need to create the time series chart. And you can see here we are in this time we are just using the Landsat image. Okay, there is no band about LST. We already learn about that how we can easily make the time series chart for unready-made dataset. So it's one kind of unready-made dataset. There is no band of LST. So that's why first of all we need to create the band of LST, and this band we need to connect with our image collection. Okay, suppose in year of 2024, okay, let's go try to check how many image collection. Just I copy my collection, all of collection without median, because when you are using the median, then it's not a collection, it's just a single median composite image. Just print and use at the image and use at the size function, size, and run it. So now we can easily find out the how many images. We find out only for 4 images. Okay, so this year of 2024, less than 1% cloud cover, we find out that only for 4 images. So when I make the time series chart, we can only find out the 4 values or 4 temporal chart about that. But when you increase the time period, or I already discussed about that, how we can easily make the annual or monthly time series chart. Okay, for another code, basically NDVI, EVI, or SAVI at the same time, I will show you that. So this type of things you also try to apply in here and make the monthly LST chart or annual LST chart, and then further face any problem, then I also guide you. Okay, so in this case my image collection only for the 4 images between this time period. So now this is my image collection, and this image collection there is no band about LST. So first of all I need to create the band of LST and then connect with my image collection, then we can easily make the time series chart. So let's go try to edit. So just take a variable, okay, I just take a variable, suppose add LST. Okay, and create the function keyword, put the element, suppose image. So now I just create a function, okay, and create this element name img. So using this element I just calculate the LST. So just we are applying the same process for calculating the LST. So just let me copy from here. So from here all of step is the same. just copy. Okay, just take copy from here, just copy. Okay, and then paste here. So in this code, just I need to change something. Suppose in this case I put the element name is the img, so all time I need to apply the img. So I calculate the NDVI using this element, and visualization dot need, just I comment, or you can also remove it, it not need. And then I can compute the maximum value of NDVI, don't need the print, I just comment. I calculate the minimum NDVI, just print, it not need. Calculate the proportion of vegetation, then calculate the emissivity, then calculate the thermal, and finally calculate the LST, and I put the rename as a LST. Okay, it not, just I remove or comment. Okay, so now I just return this function, return this image, add bands, just put here the LST, okay, this variable. So now I create a function, this function calculate the band of LST, okay, and it's stored in this variable. So now this function I need to connect with my image collection. I already check it, they are only for the 4 image collection, I want to connect. So for connecting, just use the map function and put the function variable name. So now if I just check it, all of images, basically they are only for the 4 images, and all of images add a new band, and this band name is LST. Okay, so you can say I add the new band of LST. All of images, it added the new band, and this band name is LST. So now my image collection, I create my image collection and also add the band of LST. So now I can easily apply the chart function, we already discussed about that. So just write the function ui dot chart dot image dot series, this function. So now here you can see image collection, I already make the image collection, they are the total 4 images, and 4 images I want to compute, make the time series chart for only for the LST. Okay, just I put here the select function dot select and put here LST, so LST. Okay, so now region, your shapefile variable name, which is ROI. Reducer, I want to compute, suppose maximum LST or minimum LST or average LST. Suppose I calculate for mean or average LST. Okay, then scale basically resolution of your satellite imagery, resolution mainly 30 meter. Okay, for Landsat. X property, put the X property system time start default. So now this whole things is stored in a variable. So just take a variable name, you can put any name as a variable. I put the name suppose chart, and now print the chart. So just use here the print function and use here the chart, run the code. So now the chart is apparent. So you find out this type of chart here, you can see, okay, only for the 4 images in the chart. So 1 2 3 4, we find out only for the 4. But if you increase the time period, suppose I just put the time period from 2015, okay, from present time 2024 or 25, suppose 04 13. Okay, so now it added the all of image collection and then make the chart. So further you also try to create the annual or yearly time series chart of LST. So I also give the assignment regarding this topic. You also try calculate for LST annual and yearly. Okay, so you can see, find out this type of image collection, this type of chart. And if you check how much image collection, you find out 66. Okay, so between this time period, less than 1% image, we find out the 66 image collection. So now this 66 image collection you try to convert into annual as well as a monthly and represent the chart for annual and monthly. Okay, so also try. So now it show this type of we can easily find out. Just you can also download the data also from here. Okay, download the CSV file format, and you also try for annual and monthly, then it will be also look more better. Okay, so this is the way to make the time series chart, as well as you also add the title or X level, Y level title. So previous class I already discussed about that, how we can easily add the title, chart title, or Y level, X level title. Same process you also try to apply. Okay, so this is the process for creating the time series chart. So it's very easy, just we are apply the same process, but in the last time we are just return this element name img I gave put. So just keep the same img, add bands with this variable LST, and I already put the rename as the LST. So further I can simply put here the select the band of LST. Okay, then we can easily get this type of time series chart. Okay, so this is the way to compute the LST and also make the time series chart of LST. Okay, okay, anyone in question, you can ask me please for LST time series chart or LST. Yes, please.
So you have defined the dates from 2015 to 2025. So while uh, putting the dates, we have to be conscious that which Landsat data we are using. Like for Landsat 8, we can have data from 2013 till present.
Yes, yes, yes. So Landsat, you can see Landsat 8 is available from 2013 to present. Sometime when you work with historical, suppose I want to make the time series chart from 2000, suppose 2000 to 2025. Okay, then we need to combine. Okay, so this process will show you that how we can easily combine. Suppose I make a image collection, I combine Landsat 4, 5, 7, 8, 9, and create the image collection. Then this image collection I just use, then we can easily create the time series chart or make the analysis from 2000 to 2025 or 1990 to 2025 or any time period. Then we need to combine, suppose Landsat 4, Landsat 5, Landsat 7, Landsat 8, and Landsat 9, we need to combine. But now Landsat is available only for the 2013 to present time. We can easily use this range, but when you work with make the other range, and then we need to combine. So I'll show you that how we can easily make the combine of the image collection, then you also try to apply. I hope you can easily get the
Okay,
idea.
sure.
Okay,
Kindly, please.
okay, I'll just show you that how we can easily combine the image collection Landsat 7, Landsat 5, Landsat 8. Okay, it also possible to create at the same time. Okay, okay, so now we find out this type of map for LST. Basically this type of place we find out the high temperature. So now we try to compute for urban heat island for this study area and detect where we find out the high temperature or which place is more warmer than the nearby region. Okay, so if you check, okay, so I simply search here urban island. So we find out you can see they also calculate the LST. Okay, okay, they also take the data from Moody's or Esther. Let me check. Yeah, so if you check it, suppose you can see the urban heat island. So basically in this case, if you are just compute this formula, so urban heat island equal to LST minus average LST divided by standard deviation. Okay, standard deviation. So if you just compute this equation, then we can easily find out that urban heat island. Okay, so let's go. In this case, we need to compute the mean of LST and also compute the standard deviation of LST. Then we can easily compute the urban heat island. So let's go try to apply this formula. We already calculate the LST. So now urban heat island. And this formula is that LST minus average LST or mean LST divided by standard deviation LST. Okay, so now from this map we already make the LST map. So from this LST map we need to compute the average LST and also compute the standard deviation of LST. So same process we try to compute. Just take a variable, suppose average LST. You can put any variable name and call this LST. Basically it stored this LST map. Okay, and apply the reduce region function to compute a statistical value any specific boundary. And I want to make a dictionary and put the reducer. I want to apply ee dot reducer dot mean. Okay, so now it's computing the average value of LST. Okay, mean, just put the mean. And then geometry basically a shape file which is ry. Then put here scale is the resolution 30 meter for Landsat. So now we find out, so just print the average LST value for my study area. Just I copy and run the code. And if you check it, it show the dictionary. You can see dictionary. We find out the 33.05 degrees Celsius average LST for this area of interest. Okay, so now I just need only for this value. I don't need the dictionary, I don't need the list. So same process, just apply the values and get. So just put here the dot values. So now I extract the value as a list, and from this list I just take the first item, put here the 0. So now it's computing. If I run the code, I just get the result as a computed object, but I need to use it as a number. So just I put here ee dot number and also close the parenthesis. Okay, so now run the code. Okay, so now I find out this value. This is the average value. I also need to compute the standard deviation. I just copy the same code and now compute the standard deviation. Just change the variable name, suppose std lst, and I also change it here, suppose std dev. Okay, and also just compute the standard deviation of LST. Just run the code. So we find out the 2.09 degrees Celsius standard deviation of LST for this study area. So now we are just applying this formula after computing the two value. average and standard deviation value of LST. Take a variable, suppose urban heat island, USI, and then LST. This is the subtract with average LST. So average LST, just take copy and paste, and divide with standard LST. Just copy and paste. So let's go try to visualize this layer of urban heat island, USI, and run the. So we find out, you can see as a grayscale color. So in the grayscale color, if you check, we find out the white color. This type of place is the high temperature than this type of nearby black color. So now if you check here, we find out this type of gray color without coloring. So we find out this type of white color, it find out the high temperature or warmer place than this type of black color. Okay, this type of black color. So urban heat island is one kind of phenomena where cities experience the significantly higher temperature than surrounding area. So this type of place we find out the low temperature, but this type of white color we find out the high temperature. If you want, you can also add the color or display the urban heat island map. So for that, just click on here, or also export the map as a gray color, and then further you can also add it. So you can see it show the LST, okay, default name. But if you just rename it, just use here the dot rename and put it suppose USI and run the code. Okay. So urban heat island. So suppose I want to add the color. Suppose I want to put this type of blue color, and also put suppose this type of red color. Just I keep the same. Basically 0 and 1. Suppose 0 is not urban heat island, 1 is urban heat island, and 0 show suppose this type of blue color, and 1 is show this type of red color. Okay, so just we make one kind of classification in this case. Okay, suppose 0 is indicating about the lower temperature than this type of red color. Okay, so this red color work as the urban heat island place. Okay, and this type of place we find out the blue color, we find out the low temperature than this type of red color. So you can also stressing or keep the same. Okay, just import and copy the variable name and paste after the variable name in here. Just paste here and put the layer name, suppose USI, and run the code. So now we find out this type of map of urban heat island. So now if you want to check what's the impact, where is the high impact of urban heat island and where is the low impact of urban heat island. So that's why you also use here that UTFVI, urban thermal field variance index, and we can easily get, this is the formula about that, LST minus average LST divided by LST. Then we computed the effect of urban heat island, where is the high effect, where is the low effect. Okay, if you check it, okay, let me show you for another paper. So if you check it in the R1 R1 thermal field variance, this is the same formula, LST minus average LST divided by LST, and basically you can see if you find out the value less than 0 or negative value, there is no effect of R finite island. Okay, this is the range, it is the weak, then middle, and high positive value indicating about the high effect. Negative value of R1 thermal field variance index, it indicating about that there is no effect of R1 heat island. Okay, and high positive value indicating about that high effect of R1 heat island. So further you can also make this type of classes or classification of your R1 thermal field variance index map using Google Earth Engine is also possible. So I will show you that how we can easily make the classification. So this thing I will also show you for the 7th number class for NDVI classification. Same process. We are just applying this type of range, specific range, and then we just make the classification. So this type of things we can also do. So let's go try to calculate the R1 thermal film variance index. So average LST already calculated. So now we can apply this formula. So for that, just take a variable. Suppose UTFVI, you can put in a name as a variable, and in this variable we are just call the LST dot subtract with average LST, and then divide with LST. Okay. I just put the rename it's a UTFVI. So now add the layer, map.add layer, and call the UTFVI and run the code. So we find out this type of, okay, let me try to tracing. So just apply without color. Okay, so you find out this type of map without color, such gray color. So this type of white color pixel, okay, white color pixel indicating about the impact, okay, and this type of black color pixel, it's indicating about there is no impact of urban heat island. Okay, there is no effect. So if you check the pixel value, suppose click on inspector tab, I just click, suppose just click on here, and now check what is the value of the R1 thermal field variance index. We find out the negative value. Okay, so negative value, it's indicating about the there is no effect of R1 heat island. So if you check it, suppose this type of white color plus, just click. So now you find out the positive value. Okay, you can find out the 0.1. Okay, so you can see in the Dhaka city, almost all of place we find out the effect of urban heat island. Okay, just only some, suppose you can see this is the water body, so that's why we find out the low temperature, this is the water body, also this is the water body, and we also find out this type of place, we find out the vegetation, so that's why it show up this type of black color. Otherwise all of place we find out that urban heat island effect. Okay, so further you also export as a download this map as a GOT file format, and if you want you can also use the ArcMap or QGIS software to add the visualization, or if you want you can also make the classification, just create this type of class. Okay, non, weak, middle, strong, stronger, strongest, strength of urban heat island or effect of urban heat island, and also create this type of map. So this is the way to compute for urbanite island and also urban thermal field variance index to check where you find out the high effect of urbanite island, where is the low effect of urbanite island. And all of layer we simply export, just apply the same process for exporting, and then use the ArcMap software or QGIS software to prepare your map for your research paper or your presentation. Okay, so this is the process to working with LST, then urbanite island, and also urban thermal field variance index. Okay, anyone in question, please? Yes, please.
Sir, basically, urban heat island is the temperature difference between urban and the rural areas, right?
Yes, but in this
Here
case,
we are,
urban heat
yeah.
island. So basically, in this case, for the Dhaka city boundary, it's all the full boundary is the city. Okay, so that's why we try to identify, suppose some water body or some vegetation. So this type of place we find out the lower temperature than the concrete or building, okay, or road or construction area. We find out the high temperature. Okay, but if you compare
So
it
please,
urban and rural, then we can easily find out this is the urban, this is the rural area. Rural area is the low temperature, urban area is the high temperature. We can easily identify. Yeah, please.
yes, sir. So can you say that this is LST anomaly?
Yes.
Okay. And sir, like for the Dhaka city also, not all the area is the city area. Some part must be rural also.
No, it's almost all of the city area in the Dhaka city. Basically, in this time I take for the Dhaka city boundary. Okay, so not Dhaka district or Dhaka division. Okay, we take the main city.
Okay. So only the city.
Yeah, only for the city. But it when you work with Dhaka district or Dhaka division, then we also find out some rural area, and then this type of rural area is not much higher temperature. Okay, so that's why we can easily identify.
So in the case of district, sir, do we need to take the buffer or something?
Yes.
Okay, sir.
So you can see this is the urban area. So we find out this type of place um is the high temperature than the near periphery, this type of place. Okay, because this type of place have the water body or vegetation or others, but this type of place for the concrete or build up area. So that's why you find out the high warmer. Okay, this type of is more warmer, more temperature than this type of place, this type of blue color place. And if you check the impact, so this impact almost for full city. Okay, other without some vegetation area or without some water body area. Okay, we find out this effect almost everywhere in the Dhaka city boundary. We find out. Okay. Okay, and you also try to export all of those layers and also create the map using ArcMap QGIS software. So I'll just send you this type of code. You also try to practice for your own study area. Further, if there's any problem, I'll also guide you. No problem. Okay. And I also send you all of reference paper. You also try to read. Then I hope you also get the more better idea about that LST and urban heat island or urban thermal. You can easily get a lot of idea about that. Okay. Okay, so let's go try to discuss about that how we can easily remove the cloud and haze from our satellite imagery using Landsat or Sentinel. Both of imagery I will try to show you that. Process is the same. So let's go. Just open the new code editor. Okay, just import a. Okay, so let me try to import the Dhaka city boundary again and keep the name, suppose RY. Simply search here, suppose Sentinel.